Hello to all of you. We are going to be working on calculations involving the mole. How do we convert between grams and moles? How do we figure out the number of particles in a certain number of grams? And also some multi-step calculations at the end. So we can't directly measure or count the number of particles when we're working in the lab. We can measure masses though. So we need to have this link between the number of particles that are undergoing a reaction and the masses that we have. So that's where this mole comes in. So the mole represents a certain number of particles. And this is called Avogadro's number. Okay, he's the one that was given credit for this work. And it provides the connection between the number of the particles or formula units of a substance. So 1 mole is equal to 6.022 times 10 to the 23rd particles. And particles could be atoms, number of ions, number of molecules, the number of formula units. And formula units here have to do with the number of ionic compounds, essentially. So the first thing we're going to do is convert between moles and particles. And this is where we're going to use the dimensional analysis that you practiced over the summer. So when we go to convert between these two, just like you would convert any other unit, we're going to use that relationship or that equivalent between the 1 mole and then Avogadro's number. So how many atoms are in 0.25 moles of neon? Okay, neon is monoatomic, so that's the only atom that's present. So we're going to start with what we're given, 0.25 moles. And I'm going to specifically label it neon. Okay, and then in here, just like in dimensional analysis with regular units, we're going to be plugging in the relationship. I have moles that I'm starting with, so 1 mole of neon is going to be equivalent to 6.022 times 10 to the 23rd atoms of neon. Okay, and then I get to the unit that I'm looking for with those atoms of neon. One little thing, when you go and plug this into your calculator, I'm just going to write this below, you would get this number in your calculator. And just like in dimensional analysis, you need to use the number of sig figs that you started with or that were given to you. So because I only have 2 sig figs in this 0.25 moles, I'm only going to make sure I show 2 sig figs in my final answer. So this is going to be 1.5 times 10 to the 23rd atoms of neon. And that would be my final answer there. Okay. Feel free to pause the video and try out the next one on your own, but I'm going to go ahead and go through this next one. So this says, in this case, how many moles of sodium chloride, and remember sodium chloride, you're going to need to know the formula, NaCl, are present in a sample containing the 9.6 times 10 to the 23 formula units of the sodium chloride. So we're going to start with that given amount. So I have 9.6 times 10 to the 23rd formula units, and this is of our NaCl. Okay, in this case, I'm starting with the number of particles, or in this case, formula units. So I'm going to put Avogadro's number in the denominator. So I have my 6.022 times 10 to the 23rd formula units of my NaCl. That is equivalent to 1 mole of NaCl. So when you go ahead and you plug this into your calculator, you're going to round to 2 sig figs. You're going to see that many formula units of sodium chloride is equivalent to 1.6 moles of NaCl. And that would be your final answer on that one. So this relationship between 1 mole and Avogadro's number is going to be used to convert between number of particles and how many moles we have. Now, we still haven't started talking about masses like we use in the lab, and that's where this next part comes in. Molar mass is going to allow us to do that. Over the summer, you worked with adding up the mass of various compounds using the atomic mass units from the periodic table. Well, that value of a atom or a molecule or a formula unit is always going to be equal to the molar mass of that same substance in grams. So the molar mass is equivalent to the grams of a substance per every 1 mole of the substance. You need to know that definition for molar mass. Now, one thing that's in your reference tables is this equation. It's also given in your Regents reference tables. It looks a little bit different. But this would be the number of moles. This would be like your given mass, like what was measured in the lab itself on the balance. And then your molar mass is always going to come from your periodic table. We're going to use dimensional analysis for this, but you do have that equation if you need it. So if you look onto the next page, we are going to convert between our grams and our moles. So in this one, how many moles are present in 60 grams of sodium hydroxide? We need to know the molar mass of it. So whenever grams are going to be involved, and we are going to be involving moles as well, we're always going to need the molar mass. So in this case, I'm going to need my molar mass of my sodium hydroxide. So I'm going to be looking at in here, I have 1 Na, and you can pull up your AP periodic table in front of you while you watch this so you know where these numbers are coming from. That has a molar or a mass of 22.99. And again, in your periodic table, it's in atomic mass units, but because of our definition of molar mass, we can also do this in grams. And then I have 1 oxygen, which is 16.00, plus I have 1 hydrogen, which is 1.008. When you add those together, I go to the hundredth spot here, which would then give you 40.00. And this unit specifically would be in grams per 1 mole. So every 40 grams of sodium hydroxide that we have, that's equivalent to 1 mole of it. So now we can use that in our dimensional analysis. So again, starting with what we were given, we have 60 grams of our sodium hydroxide. Okay, I started with grams, so I'm going to put grams in the denominator. So I'm going to have my 40.0 grams of sodium hydroxide. That is equivalent to 1 mole of NaOH. So now from there, it's just your division, and we're rounding to the 3 sig figs that we started with. So that will get you to 1.50, don't forget the 0, moles of NaOH. And that would allow us to then go on and do various calculations that we'll do later this unit that would help us, again, take those 60 grams and maybe figure out how much of a certain product a reaction could potentially make involving that, and so on. So feel free to pause it for a second, or you can follow along with me for this next example. So how many grams in a sample of potassium carbonate that contains 0.125 moles of it? So this is where you're going to have to know your equation writing, or formula writing, sorry. So potassium is +1, carbonate is -2, so this is going to be K2CO3. So you have to be able to get that formula correct in order to get the molar mass of it. That has a molar mass, if you add it up on the periodic table, of 138.21, and that would be in grams per mole. So for every 138.21 grams of this potassium carbonate I have, I'm going to have 1 mole of particles there. So from here, again, I'm going to start with what I was given. So 0.125 moles of K2CO3. Okay, I started with moles, so I have to put my 1 mole down here in the denominator. And then my molar mass is going to be what it's equivalent. So 138.21 grams of K2CO3. So then when you go ahead and you multiply those, rounding to the 3 sig figs that we were given with the moles, I'm going to have 17.3 grams of K2CO3. Okay, so that covers just simple conversions between moles and grams. I'm going to stop this video here, and then the next video is going to go over some other details of this process that you need.